there's other formats coming along that seem to meet that need in a more precise way. Vector tiles are really produced for doing 2D mapping. There is a standard out of the Open Geospatial Consortium that really is 100% focused on 3D mapping, volumetrics, things like buildings, but also stuff like LiDAR. There's client implementation of it in the Cesium.js. It's a spinny globe widget that you can put into your web pages in JavaScript. It might be that it goes into vector tiles. It might be that these other formats like the OGC 3D tile format instead pick up the slack for folks who really want to do point cloud shipping.
Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. My guest on the show today is Paul Ramsey, and he comes to us from a company called Crunchy Data. He's going to be talking a little bit about his involvement with PostGIS, which is an extension for the open source PostgreSQL database. We've actually done an episode on this before, so go back through the archives, find that. If the name doesn't immediately ring a bell for you, it'll help you out. Listen to that before you listen to this episode. So we're going to be talking about the extension he helped build. We're going to be talking about vector tiles, and we're going to be talking about one of his most recent projects called PG Tile Serve, which lets you serve vector tiles directly from the database. Just before we get into the interview today, I want to take a few moments here just to thank our sponsor, GraphHopper. So GraphHopper are the creators behind a super fast routing optimization engine. So this is a directions API that you can build your own application on top of. And the problem that they're solving is often referred to as the traveling salesman problem. So given a list of locations, what is the optimal route that visits each location and returns to the starting point? So GraphHopper is doing this for multiple vehicles of different profiles, different types. So if you're interested, you can get a basic idea of the service GraphHopper provides by going to graphhopper.com/maps. And yeah, there's a little web interface there that you can play around. You can see how fast it is, and it's actually quite interesting. Or if you really want to get your hands dirty, you can go and check out their routing engine on GitHub, which they've released under the Apache license. So thank you, GraphHopper. I really appreciate your support. Paul Ramsey, welcome to the show. Thanks so much for taking the time to do this interview with me. I think I've found you through several of your blog posts that you've done for Crunchy Data. So you're working for a company called Crunchy Data at the moment, and you're doing some really interesting work around vector tiles. You've created this thing called PG Tile Serve, and we're going to dive into that later on. But first, I really want to talk about PostGIS, because this is something that Crunchy Data focuses on. This is a big part of your work at the moment. And back in 2001, you had a research company called Refractions Research. And you built like the first ever spatial add-on to Postgres. Can you tell us a little bit about that before we dive into this vector tiles topic?
Sure. Back in 2001, I was running a consultant company which worked primarily for the British Columbia government here in Canada. We did a lot of work in geospatial. That was our bread and butter, and we were hired to do a data analysis project, a province-wide project that was going to take all 20,000 third-order watersheds in the province and produce a large suite of statistics about each of those watersheds. And it was going to require a great deal of processing. And at the time, top-line CPUs ran at about 300 or 400 megahertz. So we were looking at multiple days, like well over 2 months worth of continuous processing time to make this work happen. And the systems we were using to do the processing weren't 100% reliable. They'd occasionally crash and stop. So the work of babysitting all these, at that time, Sun Spark stations as they were doing this grinding and making sure they actually did the work was quite laborious and unpleasant until we realized that we could store all the intermediate data and the state of the processing from each computer on a single centralized database. And we chose Postgres as that database. And so we used Postgres to synchronize all the work, and all the SunSpark stations chewed away into their processing, stuffed the intermediate results as blobs into the tables and all the statistics into the tables. And eventually we were done, and we could run summaries off the tables and generate our final result and deliver it to the government. But as we were doing that, we looked at all these blobs in the database, which were effectively polygons and points and lines, but the database had no way of knowing that. And thought, boy, this would be so much easier and so much more gratifying if we could reason about this binary data, knowing what it is, knowing that it's in fact geometry. That motivation kept coming back as we did projects further down the line. We'd find ourselves managing, big directories full of shape files and thinking, this would be so much easier if it was all just in one table. And then we could just, instead of hunting for the shapefile we wanted, just do a query and use the attribute we knew we needed to get the particular records we wanted. So in 2001, when we had a recession-induced slowdown in paid work, we took the time to run some experimental coding projects against Postgres, trying different ways of implementing spatial types. And the type which won out, a custom type using Postgres's type extension mechanism and binding to Postgres's internal extensible index system, was what became PostGIS 0.1, which was released in May of 2001. That release was the first open source geospatial database, for sure. There was at the time only one of two legitimate spatial databases that existed at all. Oracle 8i had come out in a similar time frame and provided decent integration of the spatial type with the rest of the types. So it acted like a real spatial database should act. But I think because it was the only thing that was available that was quick and easy to put on systems, it got picked up by the rest of the open source community very, very quickly and became, in many respects, sort of a default data source that anyone would implement as soon as they implemented their software. We implemented the first connector of PostGIS to map server, so it allowed us to produce online web maps very, very early on in 2001. But projects like QGIS, which is now globally known as a desktop open source JS, the first data source that it supported was the PostGIS data source. It then later got around to supporting shapefiles, and PostGIS was the first thing it supported. And saw the same thing on the Java side with GeoServer. Basically, when a new project came on, the first thing it would do was add support for PostGIS.
Well, firstly, I want to thank you for that introduction. It was really helpful. It's really set the scene for me, and I'm sure also for the listeners. And secondly, I want to say thank you again for your work. I mean, this is a piece of software that I've used. I know that thousands and thousands of other people have used. It's a really important back end for lots and lots of other open source software. So thank you so much for making it. It's much appreciated. Okay, so we've established that you're an expert in this. And you'll have to forgive me here during this conversation. I'm sure that I'm going to use PostGIS, Postgres interchangeably.
That's one of the things that my colleagues at Crunchy find amusing about the spatial side of the business, is that when they come to conferences of spatial people, they find people constantly talking about putting their data into PostGIS. And they of course are the core Postgres developers, so they're kind of get their backs up. Why are you talking about putting data into PostGIS? You're putting it into Postgres. So yeah, it's not uncommon in the spatial world to use Postgres and PostGIS interchangeably.
I'm pleased that I'm not the only one. That's a good sign. Okay, so I want to talk a little bit about vector tiles, and then and I'm hoping that we'll sort of lay the background here for some of the listeners. What are vector tiles? What do they do for us? How should we be thinking about them? And then I sort of want to move off and talk about PG tile surf. So perhaps we could start there. What is a vector tile?
Yeah, and I'm going to have to do my unfortunate usual thing and back way into it from a long distance, because I don't think you can talk about vector tiles without talking about sort of tiled maps in general. You can't talk about tiled maps in general without talking about image tiles, which is where we started from. The first sort of interactive tiled maps came out 2005. That was when Google Maps was introduced. And it sort of led the whole GIS industry to question their assumptions about how we should be delivering maps on the web. And image tiles still haven't gone away. You'll still see them used for things like satellite imagery, anything that has sort of a continuous color gradient as opposed to specific features. But they've been supplanted by vector tiles over time. In 2010, people first started noticing that the tiles that Google was sending to Android web maps weren't the same as they used to be, that in fact Google was sending vectors back to Android. And Google was doing that for very good double-pronged reasons from their point of view. First of all, if you're sending data to a mobile device, you're sending it over the cellular network. and you want to send as little as possible to the highest effect. Secondly, when you're sending data to a mobile device, the device, unlike, say, the screen sitting in front of your desktop computer, the mobile device is, from a point of view of orientation, very, very flexible. And one of the things you might want to do with your map is re-render it according to the orientation of the device. Pointing north, make north always be the front of the device, something like that. Be able to handle rotations cleanly. Be able to handle extra data beyond just the base map. One of the issues you have when you render a base map into images is that for the base map to be useful, for it to be legible, you have to label things. But that means the labels are rendered into the image along with the features. So if you lay anything else on top of that base map, you run a risk of occluding the labeling and making the map, again, illegible. So to get a really nice user experience where you have both the base map and extra layers brought on top, you really need to do all your labeling at the end once you know all the stuff that's going to be on the map. And that implies that the renderer is happening much closer to the user. And one of the reasons why, say, Google or anyone else didn't do vector tiles immediately, like, oh, I have this idea of having a tiled map, and I'm going to cut things into neat 2x2 squares and send them down. The reason why they started with images and not vectors is because the devices at the far end just weren't capable of doing the rendering. You really required a big chunky engine on the server side to do the rendering, particularly if you're rendering something which was fairly dynamic and not rendering things which were already pre-baked. So it really took the existence of web browsers that had enough horsepower, JavaScript engines that had enough horsepower to do the rendering right in the web browser, do the rendering right on the mobile device for it to make sense to send a vector tile back to a client. But once you had that infrastructure there, once you had systems that were strong enough to do the rendering on the client side, all of a sudden a whole lot of opportunities open up when you're sending vectors as opposed to sending rasters. You can get a great deal more interactivity when you've sent more things down than just the features themselves. Because a vector tile doesn't include just the points, the lines, the polygons. It also includes attribution about those points, lines, and polygons. That attribution is used to control the rendering, but it's also still sitting there to be used for things like querying. So you can build quite complex, totally client-side user experiences if you've sent back enough information on the vectors for the application to be able to do those things. It's a feature which was never really available when you had image tiles. Image tiles, the best you could handle was maybe doing some hacks to get a rollover. But everything else, if you wanted to run queries, if you wanted to restyle the image so that you could see a different chloropleth or highlight a different feature you were cared about, you would have to go back and round trip to the server. And when everyone was doing web mapping on desktops with relatively good connectivity, that was an acceptable compromise to make. But when you have to round trip everything through a cellular connection and not only deal with the size of that straw, but deal with the latency of that straw, the more stuff you can push down to the client, the better. So having a vector tile just opens up a whole lot of possibilities in building web maps and leapfrogs through a whole bunch of the limitations that we had to deal with when the only option was producing image tiles.
So I guess you've laid out a whole bunch of great points there around vector tiles, where they come from, and why they're better or have other advantages, I should say, than image tiles. What does the process look like of creating them? Is it the same idea where we have a back end, a database, and we have some process sitting and chunking out these tiles and putting them in a huge file or a file structure somewhere ready to be served out? What does that process look like of building vector tiles today?
Until relatively recently, the bias in producing vector tiles has been big batch processes. The first published standard, open standard for a vector tile was a de facto standard that Mapbox produced in 2014, the Mapbox vector tile format. And that's the format which has become the de facto across the open source world and to an extent across the larger geospatial industry. The exceptions being tightly bound systems like Google or iOS or so on that have their own internal formats. But for interoperability, all of open source and to a large extent Esri actually follow the Mapbox vector tile format. So that's the binary encoding of these tiles. Mapbox provided and provides a whole bunch of tools for producing vector tiles in the open source domain. And they really lean upon a batch process idea. You feed the tile producer with a whole bunch of raw data, and it spits out a whole pyramid of tiles from the lowest resolution to the highest resolution stored in a SQLite database. And then you put that SQLite database online, and it serves from that static cache. And that's fine as long as your data doesn't change.
I was just about to say, so that leads us with all those problems. If we have any kind of dynamic data that this is being based on, we have all those sort of caching issues that we have with image tiles, I'm assuming.
Yeah, that's exactly what happens. And unfortunately, a lot of folks, and the same workflow was oddly adopted by Esri in some of their early products for producing both image tiles and now vector tiles, which is the idea that we'll produce a map cache or a tile cache and then publish the tile cache. And then organizations which do, in fact, have dynamic, volatile data end up building these really unfortunate workflows where, every night at 2 a.m. we turn on the cache generator and it grinds for an hour and a half. And then at 6 a.m. we upload the file. When in reality, most of these use cases would be perfectly happy if you generated the tiles on the fly from the raw data. Things that have changed since 2001 when PostGIS was invented, or from 2005 when Google Maps came up with tiles, the quantity of processing power available to any given organization has gone up by several factors of 1,000. Clouds have come along, so even there's really no capital burden to spinning up extra processing as required. So computing is cheap. It's relatively easy to do. There's really no reason not to generate dynamic tiles. And one of the things that I think PostGIS lends to this process is that, in addition to having spatial types and spatial functions, so you can do fast random access and sort of treat it as a spatial backing store, it's got over 300 other functions in it beyond the basics. And those other functions do things like clustering and aggregation. You can do buffers and unions. You can do layer overlays. You can generate fields of random points. You can run Delaunay triangulations. You can build Voronoi triangulations. You can combine multiple layers. You can find all the fires within 500 meters of the control station. You can find all the nearest neighbors to another, to a different set of layers. All the questions that you can ask and answer in traditional GIS can be asked and answered inside the PostGIS engine, right next to where the data is actually stored, using spatial SQL.
So we have this back end, we have this incredible amount of power and functionality, and we know that caching tiles is perhaps going to lead to an unfortunate workflow, as you phrased it before, for a company that has dynamic, volatile data. And this is all, of course, very leading because you've got the answer for us.
Kind of, I do, yeah. One part of the answer is, in addition to all those analytical functions, PostGIS has over the years accumulated a large collection of format functions. So from back in the early 2000s, there were formats which will ingest and create GML formatted data and KML formatted data and X3D for folks who want to walk through the data in a 3D browser, and GeoJSON input and output. And most recently, 2.5 years ago, we added support for outputting data in the MVT format. There's a function called st_as_mvt, which takes in a set of records and spits out a protocol buffer formatted MVT file. So if you send in a bunch of records which are shaped in a neat tiled square for a particular area, it will spit out effectively a vector tile. So anything that you can produce that produces a set of records, anything you can run that produces a set of records, can be fed into the MVT function and will spit out the tile. So the database is perfectly capable of taking in arbitrary queries or just queries against tables and spitting out appropriate tiles, which is great for people who want to type in SQL. But what we really want to do is feed the end user and feed end user applications. And end user applications use web map components. In the open source world, there's OpenLayers, there's Leaflet, there's more recently Mapbox GLJS. These are all web map components that give you sort of what you'd expect out of a Slippy map. They'll run in mobile, they'll run in the web browsers. They give you an infinitely zoomable, infinitely pannable map based on tiles tiles requested from the network. And all they expect is, in order to operate, is a URL, which gives them the address of the server and will listen to requests that provide a zoom level, an X and a Y tile coordinate, and spit back a tile. And they operate over the web protocol HTTP. So there's a gap in between these web map clients, which speak HTTP and expect to send in tile URLs, and the server, which speaks SQL and expects to be asked questions in geographic coordinates. And inside that, into that gap, we've slid the smallest possible piece of software we could write. We want to do as little as possible to do the translation. Incoming tile request on HTTP gets turned into the equivalent SQL that gets run on the database. The result is a binary buffer, which is then sent back to the web client. And that piece of software, that little narrow piece of software, is PG TileServe.
So if I could just try and summarize just for a second here for the listeners. So what you've built is a piece of software, PG TileServe. I install it on my machine. I'm assuming I have to match, that version up with the version of Postgres that I'm running, install it on my machine, and then that will take in HTTP requests, feed it over to the database, which has all the functionality to convert anything in a table essentially into vector tiles and spit them back out. I have a dynamic tile server right now as soon as I install this on my machine.
That's correct. Yeah. And we've got builds for Linux, for Windows, for OS 10 online. There's no particular install step. The code is written using Google's Go language, which produces fully independent binaries, so they don't have any dependent libraries. You don't need to install a whole environment to run them. It's just an executable. So you download the executable for whatever your operating system is. You set an environment variable to point to your database, and then you run the program. And the program connects to the database, reads through and finds the tables it's allowed to access, and publishes them on the web.
That is amazing. And of course, I've read some of your blog posts. I haven't tried this myself, but it seems like you've done a really great job of documenting it. And it sounds incredible that I can just do this and have dynamic tiles straight from the database. So I guess the next question is, how do we restrict access to this? How do we tell PG TileServe, make tiles out of this, don't make tiles out of that? Does it go through my entire database? Will it all of a sudden be open to the web?
We really believe in using the database and all the strengths that exist within it. And one of the things the database has is a set of roles and permissions. So what you do is when you set the environment variable to tell PG TileServe which database to connect to, you tell it which user to connect as. And then inside the database, you give that user permission to read only the tables you want it to read and to run only the functions you want it to run. And that way, there's no way for anyone to sort of find a crack in PG TileServe's implementation. There's no such thing as a SQL injection attack when the thing that's running the SQL doesn't have any powers that you don't want it to have. So you provide access to the tables you want it to see, and you don't provide access to the tables you don't want it to see.
Can you give me an idea of how many? This is going to be a difficult question. I'm not even sure if it is going to make sense, but I'm going to try it anyway. So if I was the admin of this database, I'm like, whoa, am I opening my database up to an unknown amount of traffic? Will it crash? Will it go down? What can it handle in terms of traffic, do you think?
Well, you really have to parameterize that. So any given tile request, and this is where it depends a great deal on the amount of data you're serving and how you set up your map. Because, for example, if you're serving 500,000 roads and you're serving it at all scales, at some of the scales, it will be reading through every road. Other scales will be reading through 6. Now, obviously, the requests that only read through 6 will run a lot faster. So depending a lot on configuration and so on, we found that tile requests can take 30 milliseconds to 130 milliseconds. So that would be the amount of throughput you'd expect on one core, be 10 requests a second. The answer is yes, you're potentially exposing yourself to unlimited traffic if you're the kind of site that might receive unlimited traffic. Again, it's about knowing yourself to some extent. Again, one of the things we're looking at Crunchy is we sort of explore the way of building applications using this architecture is what kind of dynamic caching you'd want to put in front of a tile server like this. because, and I found this in my previous job, working for a software as a service company that produced online maps for things like newspapers who had very spiky load, was that it did not take a lot of caching to reduce the backend server load to almost nothing. All you had to do was say, okay, for any given tile, I'll keep a copy of it around and reserve the cache version for a minute. All the load issues just disappear because everyone who shares that same cache, they get the same thing. And it's as much as any given tile is as much as 1 minute out of date. So you can put a cache layer in front with a very short timeout and reduce most concerns about overloading a database to nothing. The other thing you can do, and this is one of the reasons we like a container, we've built these servers, PT tile serve and PT feature serve and future PG something serves, with the idea that they'll be run as microservices, probably within a container architecture like Kubernetes, which allows you to scale up dynamically based on load. So as a tile serve node gets pushed to the top of its usage, a second one will spawn up automatically. And we've also worked on Kubernetes deployments of Postgres. So sort of the vision for this is if you had a big enough installation, you would have, in addition to a lightweight caching layer in front, read replicas in the back. So you'd actually scale up read replicas of your database. And that's something which the container-based deployments of Postgres that Crunchy has been working on, that's what they're made for. The idea that, yes, you have a single write controller, but you can have multiple read replicas at the back end. So even if you did manage to push out and have a big enough load to saturate one, you could just bring up another.
So in the same way that we're going to use a cache here, so this dynamic tile serve that we're talking about is, if we've got high traffic site, we're going to put a cache in front of it, and that's going to alleviate some of the pressure on our back end. Serving dynamic tiles isn't just the silver bullet for everything. I'm assuming vector tiles in themselves, they're not always going to be the right answer. Can you give us an idea of when vector tiles are not the right answer?
Well, they're definitely not the right answer for imagery, even though the new standards include the ability to insert imagery. If all you're doing is serving image data, it makes a lot of sense to use just a nice old cache of JPEGs or dynamically rendered JPEGs using something like Google to pull tiles out. You might not want to use vector tiles if you're unsure of how good the client-side devices that you're serving to are. Like there's an expectation, particularly if you're serving a fairly dense vector tile, like a base map tile, that the receiving device has a reasonable amount of horsepower to do the rendering. If you have folks running on ancient PCs with old versions of Internet Explorer, you might not be able to serve them. I don't know if there's a lot of reasons anymore to use imagery for things that like schematic base maps, just because PNGs can sometimes be smaller for some cases of data, but not a lot smaller necessarily. So if you have the facility in your clients, then there's something to be said for doing the vector tile thing no matter what. It does impose an extra layer of complexity on the client-side developer. So if your client-side developers really don't need a lot, if they really just are going to have a base map and they want to do some markers, by not forcing them to consume vector tiles, you're taking away from them all the complexity of thinking about how am I going to render it. And they can spend just like people spend a lot of time fiddling with the fonts when they're writing their documents.
Yeah.
You hand the problem of now style this map over to a web developer. It might be several months before you get their noses out of that.
Hey, Paul, I'm conscious of the time here, but I've got a couple of questions left that I really want to ask you, and a couple come in from the good people on Twitter, and one of them was around data security and vector tiles. So I guess when people use images, when they're using a VMS server, for example, or serving image tiles out to people, they have that security. They know it's difficult to get the data out, to get to the raw data. But with vector tiles, I mean, we're sending a much more detailed map of the world out to people. We're sending our data out to the people that they could get their hands on. Can you say anything about the security around vector tiles?
Yeah, there's no doubt that it's easier to retrieve coordinates from a vector tile than it is from an image tile by a long shot. There's a couple things going on, though. I mean, one is you are showing them to the world. So there's kind of an expectation that the information is there. The other is that you're not actually showing the raw data to the world. Because the fidelity is really, really good, there may be a tendency to think, oh, well, this is my raw data, particularly when you have the attributes and things like that showing up on the far side. But you can constrain the attributes you send back. So probably you'll only send back enough attributes to serve your application needs and your rendering needs. The other thing which is not appreciated is that vector tiles are not perfect representations of the raw data. They are a lot more similar to images than they are to raw data. Every vector tile, just like an image, has a fixed and limited resolution. The tiles you get back, the image tiles you get back from an image web server are usually 256 by 256, or if they're high res, they'll be 512 by 512. A vector tile has a resolution usually of about 4096 by 4096. So it's higher resolution, but it's not full double precision resolution. So any vectors that get inscribed in a vector tile, they get snapped to the internal resolution of the tile. So the exact coordinate values get shifted around. So if there's any expectation of things like topological correctness, if you hope that your edges still match, all that will go away when they get stuffed through the process of vectorization. They also don't join neatly on the edges. It's a thing that people don't necessarily recognize about vector tiles, but the amount of data sent back is slightly larger than the size of the tile. It's to allow rendering of wide labels and wide line types. So it's kind of a rendering hack, but it means that recovering a full coverage of data from a set of vector tiles means not just extracting the vectors, but then dealing with all the places where the vectors overlap and cleaning up all those lines and properly snapping them together. So while it's easier, say, than doing raster to vector extraction on an image, it's not a quick 30-minute task either.
Okay, so we're not just handing our data over to the world. That's what I got out of that. It's much more complicated than that.
Yeah, you're handing something over to the world, just like you are when you're putting out images. And it is easier than images to extract, but it is not an easy pipeline to your raw data.
Another question that came in from the listeners to this podcast was Vector Tiles 3 point cloud support. So are we going to see point cloud support in the next version of Vector Tiles?
I don't know. We might. There's not a lot of demand for it in that there's other formats coming along that seem to meet that need in a more precise way. Vector tiles are really produced for doing 2D mapping. There is a standard out of the Open Geospatial Consortium that really is 100% focused on 3D mapping, volumetrics, things like buildings, but also stuff like LiDAR. There's client implementation of it in the Cesium.js. It's a spinny globe widget that you can put into your web pages in JavaScript. So it might be that it goes into vector tiles. It might be that these other formats like the OGC 3D tile format instead pick up the slack for folks who really want to do point cloud shipping.
Paul, in our previous interview, in a previous conversation, you said databases are fundamentally boring, fundamentally important, but fundamentally boring. Why do you think that is?
No pictures, and it's really clear somehow. I go to because of the worlds I straddle. I go to database conferences, and I go to GIS conferences. And yeah, the database talks are always really visually the most dull possible thing. There's code on the screens, and that's as exciting as it gets. Whereas the GIS talks always have a pretty picture. No matter how technical it is, there's always some pretty pictures. There's no getting around that. I went from a company which was all about maps and visualization, where I was the boringest guy on staff, the database guy, to a company that's all about databases. And I'm the most exciting guy on staff. I didn't have to change myself at all.
Okay, I think there's a lesson for us there. If you think you're boring, change jobs. That's what I got out of this. Hey, I really want to thank you for your time. I've really enjoyed the conversation. I've learned a ton. I need to say that. So I've really learned a lot. Thank you so much. I will be sure and put links to PG TileServe and to Crunchy Data, and of course to yourself in the show notes so people can find you. But perhaps as well as that, could you let the listeners know where they can go to find out more about you, to contact you, to get a hold of this PG TileServe?
Sure. So if you're interested in me and my writings, I'm at cleverelephant.ca. If you're interested in PostGIS, you want to go to postgis.net. And if you're interested in PG TileServe, go to github.com/crunchydata/PG_tileserve with no E.
Wonderful. Thanks very much for your time. I really appreciate it.
Thanks, Daniel.
Thanks once again to our sponsor, GraphHopper. I really appreciate your support. It's fantastic having a company like you behind us. It's much appreciated. To the listeners, if you're looking to solve the traveling salesman problem, or if you're looking to do anything with routing optimization for larger fleets of vehicles, check out GraphHopper.com. You can support the podcast by supporting them. Thank you. And that's it for another episode of the Mapscaping Podcast. My name is Daniel, and I want to say thank you for tuning in again this week. Much appreciated. I also want to thank the people that have taken the time to reach out to me on social media, find me on LinkedIn, to engage, to give their feedback about the podcast. It really helps me figure out what direction to take things in, to find out what you're interested in, what you're less interested in, how I can improve this for you. So your support, your comments, and your engagement is really, really appreciated. Thank you very much. Talk to you again next week. Bye.